All right. Questions?
I have one about the percent EE. Do you think we'll need a calculator tomorrow?
You will not need a calculator. You will neither need nor be allowed a calculator tomorrow.
So it's more so just understanding like how it would work with the reactions themselves, rather than like, oh.
No, I just expect you can do math.
Okay.
Yeah, the questions about EE will be much more in how it pertains to the stereochemistry of substitution reactions.
Oh, so you're making fun of me.
Huh?
So you're making fun of me.
Totally. Yeah.
Okay, cool.
So it'd be like 0 or 100, like how much you just
No. Right? Like if you,
We'll talk about it later. 0 or 90? It could be the same.
No, if you're missing the point. What would you do? 0.
right.
Yeah, but
So that is something everybody should probably, I mean, if you're going to take like one fact that you memorize away, a racemic mixture is 0% EE, not 50. So I saw that some on the assignment sheet you guys did. And I mean, I see it every year, and I understand where it comes from. A racemic mixture is 50% one enantiomer, 50% the other. EE then is 50 minus 50, which is 0. All right. When I say it's not 0 or 100, all right, so draw the product of that. And give me the EE of the product. Yep. All right, so got a leaving group?
Yeah.
Got a decent nucleophile? What's the temperature? So what are we going to do? All right. So if it's an SN2, nucleophile is going to do a backside attack. What's the percent EE? 96 is not 0 or 100. That's all I meant by that, right? So pure SN2 here. Good nucleophile. It's a secondary halide, but you got a polar aprotic solvent that supports SN2. Lower temperature. The reaction's going to go slower, but that's going to slow down. Like SN1, leaving group leaving to make a cation is going to be really poor. Like this reaction is going to be SN2. So every molecule of the starting, every one of those chlorides is going to do an SN2. Backside attack, inversion of the carbon that's got the leaving group. 96% EE though, not all the chlorides have the chloride forward. 2% of the chlorides are back. Okay, so with 2% of the chlorides back, those 2%, the cyanide's going to have to come from the front. So your EE is going to end up the same. Yeah, so if we do this reaction, I think I told you guys 40. Just screwing around. All right, so draw the product there. All right, so in this one, still have the leaving group, same exact molecule. Let's assume it's 96% EE. But now you don't have a good nucleophile. You have a polar protic solvent. So right, this is called a solvolysis reaction because water is going to be both the nucleophile and the solvent. I edged the temperature up. I think I told you guys 40. Like I said, I'm not going to ask 39 or 41 or 40 on a predict the product problem. You might see one on like this, a word problem, like explain what's going on. But this is going to end up being SN1. And it's basically going to be, all right, so it's SN1. You don't have a good nucleophile. It's a secondary halide, so you can make a cation. It's a little sterically hindered. Temperature's a little up. So this is going to go mostly as SN1. You could also, so then you could have one, and I think this is for people that missed whatever class it is I did this in, right? You could have something like this, potassium carbonate, or sorry, potassium cyanide, cyanide. It's Monday, right? Potassium cyanide. But now you're in a polar protic solvent. A polar protic solvent does help SN1, slows down SN2. Temperature's a little up. Basically, you're going to get the same, you're going to get the product you'd get up at the top, and you probably will get it with mostly backside attack. But this EE is going to be, for example, 30% EE, all right? You couldn't really predict that, but you might look at that reaction and say, that's not going to be a pure SN2 reaction, and it's not going to be a pure SN1 reaction. And so it'd be somewhere in between. Again, I am not going to ask you tomorrow to predict that, so as you do the reaction questions, you're not going to have to come up with something like that. But this would be a plausible thing to do. This would be a plausible word problem kind of thing, right? Like one student comes in and does a reaction this way, and hey, gets a 96% EE. Another student does this. Well, if you don't add the cyanide, you're not getting the nitrile, right? Like that's an important thing. Somebody else does it this way, chooses water, doesn't keep the reaction cool, loses a lot of the stereochemistry. So that's how EE is going to get used. If on the final exam you might see an EE question, a little more sophisticated than that, but not a lot. Like just throwing that in at the end isn't a terribly fair thing. I want to make sure you've seen it. I want to make sure you've seen the plus minus bit. So I'd like you guys to keep in mind, right, if you have one enantiomer that rotates plane polarized light clockwise, the other enantiomer will rotate it counterclockwise, right, plus and minus. The magnitudes will be the same. So if you know the specific rotation of one enantiomer, you know it for the other enantiomer. Like that's just kind of stuff you might need. I don't know, you might see it in biochemistry. You certainly will see it if you get into any kind of med chem or drug discussion, like an academic drug discussion. That help? I don't know where the question came from about EE, I forget, but like, you're down to a few hours of studying, and really it should be a few hours. You should get some sleep tonight. But don't spend it all in chapter 5.
To perform ozanolysis on an alkyne, is water necessary as a reagent?
Yeah. So this reaction, I'll go ahead and. I had a few of these in office hours, so I hope if you were there that this doesn't, the repetition's not too bad. So yeah, that'll be a good one. Okay, so ozone. Ozone's one of these reactions in chapter 8 and 9 that really I would love to talk about. Ozone is a wonderful molecule. There aren't many molecules that are both pretty and smell good and do interesting chemistry, right? Like you can find 2 of those in a lot of molecules, but not the other one. So ozone's this really sky blue, pretty molecule when it's dissolved in solution. Smells nice. And then it does some really interesting oxidative chemistry. The mechanism is fairly confusing, right? And so it doesn't exactly follow the Lewis acid-base model that I want you guys focusing on, right? Lewis base has electrons, gives it to something that doesn't have electrons, and then stuff happens. So I basically just asked you guys to memorize this, and the way to memorize it, anytime you have a pi bond like this, pi system like this, ozone is just going to cut through all of them. I keep meaning to look at this. I think it's the only reaction where you completely sever carbon-carbon bonds in Orgo-1. You'll see it some more in Orgo, you'll see more of that in Orgo-2, but carbon-carbon bonds tend to be hard to break. For the alkene, that leaves you 2 bonds shy, right? So the alkene's lacking 2 bonds. And for the alkene, you just replace the oxygen, or the 2 bonds with a double bond to oxygen. All right, so you can kind of go in here. The drawing is a little odd, but you can just sort of stick in a carbon-oxygen double bond there. Those two oxygens are not bonded to each other. For the triple bond, you're 3 bonds shy. So 1 oxygen's not going to be able to take care of that. And you asked the question, I said yes, and then didn't show it. All right. So the other thing there is then the 3rd bond's going to be to oxygen as well. So this is going to end up, I'm going to straighten out one of those. Right, so there's I've just aimed the carbonyl this way. Then this carbon, lacking 3 bonds, 2 are going to be a carbonyl to oxygen, and the other is going to be an OH from water. Let me number these. If you have an alkyne that is bonded to, if you have an alkyne bonded to an H, an sp carbon bonded to an H, you do an ozonolysis, so carbon 1 here is going to end up carbon dioxide. And it's worth, especially as you start to think about going into Orgo-2, I'm going to have more words to say about Orgo-2 after the exam. As you start to think about that, though, keeping the structure of CO2 in mind is important. It's really that sp carbon in the middle has got 2 carbonyls on it. So a fair amount of the chemistry you'll see in Orgo-2 will involve carbonyls. Carbon-oxygen double bonds. I'm having a lot of trouble with my mic, sorry. All right. Carbon dioxide does that chemistry. And so you may have read about CO2 sequestration, right? Trying to suck CO2 out of the atmosphere. A lot of that chemistry takes advantage of the fact that CO2 is a carbonyl. So things that can react with carbonyls react pretty well with CO2 usually. That's totally unimportant for this exam, really, but outside of, you make CO2 from ozonolysis of a terminal alkyne. Yep.
When you split the triple bond, do you not also get like a separate carboxylic acid that's not attached to the...
So you would, if carbon 1 here, like in an alternate reality, if carbon 1 was a methyl, then you'd end up with this carbonyl. So if carbon 1 is bonded to an H, you get CO2 out of it, because you can break the CH bond. If carbon 1 is bonded to pretty much anything that isn't an H, you get a carboxylic acid. Carbon 1 ends up a carboxylic acid bonded to whatever else the other thing is.
So if there's like a methyl
alkyne.
Do you still get the carboxylic acid, like,
Yeah, so that's what I'm saying. If this methyl is here, bonded to one, you'd get this.
and the other?
And that.
Okay.
Yeah. Trying to think of ways to label this. More? No more questions?
I usually understand its role in like reactions, but every time I see DMF, I just forget what it is.
DMF. You had the lab, right?
Have had, yeah,
I mean, you had it this semester?
not this semester.
Oh, you didn't, really? Yeah, so so DMF, that's DMS, which is not DMF. DMF here is that. Dimethyl form amide. It's a polar aprotic solvent. DMS is not a polar aprotic solvent. It's not a very polar solvent. DMSO is a polar aprotic solvent. Don't worry about DMSO, all right? If I want a polar aprotic solvent, it will be DMF tomorrow. And that's another sort of on that, right? There are clearly high, I've even written an H in there. I've written a proton. So an aprotic solvent is a solvent that doesn't, that's how I will, that's probably how I'm going to die. I'll be like 79 doing Orgo 1 for the 98th time or something. And anyway, and one of you might be the ER doctor that gets that call. So I should be nice. Anyway, so 1 second. It's been a long week already. DMF aprotic solvents are solvents that don't donate a hydrogen bond. All right. So DMF can hydrogen bond, but only as an acceptor. So, all right, there's a hydrogen bond. Water in that instance is a hydrogen bond donor. DMF is a hydrogen bond acceptor. Water can be both a donor and an acceptor. DMF, an aprotic solvent, can only be an acceptor. All right, so even though the solvent has a bunch of protons in it, we say it's aprotic. And there's a bunch of these. Like I said, I'm not going to cover it right now because, so DMSO is dimethyl sulfoxide. DMS is just dimethyl sulfide. Acetone is actually a pretty good polar aprotic solvent. Acetone's a really nice solvent for SN2 usually. Anyway, aprotic solvents just mean they're not hydrogen bond donors. Anything with an OH or an NH will be a protic solvent. All right, sorry.
The second one on this, because it was 3 different products, and so I guess that this was just because of this.
Right.
Okay. Can we go over that?
Yeah. So this is one of last year's exams. I'm not sure I'm going to get it exactly right, but I'll get the... So this is also, yeah, this is an ozone question. So you have you have an alkene and an alkyne. And so you're just going to cut through the pi bonds. So over here on the left, again, I'll number these. The alkyne's not terminal, so carbon 1, Carbon 2 are going to stay bonded together. Carbon 2 is going to turn into a carboxylic acid. Over on the end, carbon 7 is in an alkene, so it's just going to end up a carbonyl. So we're going to get formaldehyde out of that one. Three through 6 are all going to stay attached. Carbon 3 is going to end up being a carboxylic acid. Screw myself up here. Nothing happens to carbon 4, nothing happens to carbon 5. Carbon 6 ends up a carboxylic acid. No. How about I do the problem right for you? Carbon 6 ends up just a carbonyl. So three different products. I'm pretty sure when I graded that, the only one of those you had to draw was the middle one. I can't remember if I took off points if you didn't show the other two. I mean, I probably should have. Like the real answer includes all those. But a lot of time, organic chemists are guilty a lot of only caring about like the main organic component. So when you work that reaction up, formaldehyde is going to evaporate, it's a gas. Acetic acid is probably going to wash out if you do an extraction. You're never going to see it. But that heavy thing that's going to be left at the end of the rotovap is what you're interested in. For a lecture class, that's really not all that fair, right? Because you've had a semester lab, but like judging practical stuff like what the major organic thing is tough to do. Does that make sense? This is last. You want me to talk about mass spec too?
I mean, I don't really know if that's on this exam, but
Well, it might be on the final though.
I know.
And it's pretty straight. I mean, it's pretty straightforward, honestly.
Yeah.
So the question was, the person who did this experiment wanted to make this compound, desired product. All right, didn't get this compound, got this compound instead. And I asked for the mechanism for how that happened. So draw a mechanism that accounts for formation of the observed compound. And then I asked for how you would tell that you got that by mass spec. I'll do the mass spec first, right? The molecular weights are different. There you go, right? Your molecular ion is going to be different here than there. And you obviously won't have a bromine in it. Alcohols, if you want to get into fragmentation, some of you might have had people that did more mass spec in lab. You'd lose water from this one. You're not going to lose water from the desired product. So we get the observed product only. So take a second and think about how you might get that. All right. So approaching this, like it should be, I think, pretty obvious how you would get the desired product, right? This is just going to be an SN2 reaction. Methoxide comes in, kicks out the bromide. And that should suggest SN2 chemistry. You've got a polar aprotic solvent, you've got a good nucleophile, temperature's low. So then you obviously got something you didn't predict. So how did that happen? And from there, you don't really necessarily need to think about the conditions. You need to think about just what you know. And if you look at this, so going from the starting material to the product, we are going to lose the leaving group. So a substitution of some sort probably happens. And in fact, really the observed product is just the starting material minus HBr. Right? So we make an oxygen-carbon bond in there somewhere. So then the question becomes how you do that. And you've got a couple of different options. Let's think about all the options we could do. So first, we could do like SN1 chemistry, right? If you just think about this completely in a vacuum, do SN1 chemistry and have the alcohol attack. But this is SN2 conditions, which is why you do need to think about the conditions a little bit. And it's a primary cation, so that's really unlikely. You're not going to make a primary carbocation in general. All right, so one is probably out. The second is you could just have an SN2 from the alcohol. Right? Like, that's a plausible thing that could happen. But again, the conditions are SN2, and the molecule, the ion I've just drawn is a strong acid. Right? Oxygen that's protonated and positive is going to be a strong acid. That's a strong acid under basic conditions. So that's probably not good. The third possibility is you do an acid-base reaction first. And you wind up with all right, so this is just going to be so we still have a base, right? The nucleophile, methoxide, is both a base and a nucleophile. A lot of these problems boil down to anything that can be a nucleophile is also a base, and anything that's a base is also a nucleophile. Okay, so if the methoxide takes the alcohol proton, I get an O- and methanol, that ought to be about 50-50, right? I've got a localized O- on both sides, I've got an alcohol on both sides. So equilibrium-wise, that ought to be the same. And now we can do SN2 chemistry. Good nucleophile, good leaving group. And that gets us to our product. Those are really the only three options present. And so you rule number one out, option one out, because you're making a primary carbocation. It's the best reason. It's also SN2 conditions. That's a good, even if you could do SN2 here or SN1 here, probably wouldn't. You rule out 2 because you're making a strong acid under basic conditions. That leaves 3. Right? And basically what that's saying is an acid-base reaction, a proton transfer, is going to be faster than an SN2 reaction. So at the top here, this methoxide can grab the H, or it can come in here and make a bond to the carbon. It's easier and faster to make a bond to the H than to the carbon. And then once you do that, students typically don't like intramolecular reactions. So, right, a reaction where both reactive sites are in the same molecule. But they're actually usually much faster than intermolecular reactions. So the SN2 that we wanted to have happen requires 2 molecules that are not part of each other to collide. On the bottom, you've got a nucleophile and an electrophile covalently attached to each other. They can't get away from each other. Right? They're basically right next to each other. They're gonna be able to react quickly. If the molecule can adopt a conformation where they can access each other, they will. Does that help? Yep. Yep.
Can you go over drawing the energy diagrams when it comes to the overall rate law?
Yeah, I'm wondering, do we have a... I don't see one that... I'll come up with it in a minute. Tell you what, I keep doing them in water. Let's do one in methanol. Tell you what, come up with, I will eventually answer your question. First, do that mechanism, and then I'll do a few discussion points. What's the first thing that happens? leaving group leaves. So just like in an SN2, I was looking, I'm not trying to tell you anything. I was looking through old exams, obviously, trying to build the new exam. And I seem to ask a lot of SN2 rate questions with different leaving groups. Okay, a better leaving group reacts faster than a worse leaving group. That's what we're referring to when we say better and worse. All right, that is true for E1, E2, SN1, SN2, any reaction leading to some sort of rearrangement. Better the leaving group is, the faster it leaves. Okay, so iodide leaves faster than chloride or bromide. All right, so iodide leaves. We get a cation, carbocation. That carbocation is sp2. It's trigonal planar. It's flat. And obviously, if you look at the product, we have to rearrange things. The methoxy bonds to something else besides that carbon. The carbon that had the iodide suddenly gets 2 hydrogens. It's only got 1 at the start. So we have to move a hydrogen there somehow. And that's just going to be a rearrangement. And then that loses us our stereochemistry. All right, so there we have a tertiary allylic cation. That cation's delocalized, and it's tertiary here. Keep in mind, you can draw resonance structures looks like that. I've had a bunch of questions about ranking cation stability off some of the old exams, and occasionally I'll sneak one in there like that, and everybody thinks it's a primary cation. It is. That is a primary cation, but it's delocalized, and you got to consider that when you're considering the overall stability. Right? Anytime you're asked to judge stability, and really anytime you're drawing a mechanism or thinking about a molecule, you've got to consider the resonance. Resonance isn't just something we do to, tick you off early in the semester. It's an intrinsic part of the molecule. Okay, so to get to our observed product then, we've got a carbocation. Methanol is going to attack. So we got methanol on there, and then methanol takes the acidic H. That gets us our product. We're going to draw a reaction energy diagram for this. But first, I wanted to point out, you should also consider what else you might get. When you've got a delocalized cation like this, and it does SN1 chemistry, the nucleophile can sort of hit either any of the positive carbons. Right? So we could also have methanol attack here. And honestly, this double bond could be cis or trans. And then methanol would take this last proton. Right, so you'd get the methyl ether down on the left as well. Okay, so let me put some letters on this. Starting material, or you guys might like reactant. Reactant, A, B, C, product. So draw a reaction energy diagram with those intermediates. No, just R, P, A, B, and C. But if you want to. You're welcome. It's not going to be very useful to you. Do you have a sharpener somewhere? Huh? It's your eraser. Awesome. Okay, so start by putting R on there somewhere. And it doesn't actually matter, like the energy diagrams I'm going to ask you guys to write, that you can write qualitatively for a reaction. We could do computational chemistry, we could do a variety of measurements to actually place this at its energy level. But what we tend to do is just show relative stability, okay? Less stable things are higher up, more stable things are lower. Okay, so then going to A, leaving group leaves, this is generally going to be the slow step. And there's A. All right, so we're going to have a big energy of activation, and then we get a secondary cation that's quite high in energy, not very stable, right? That rearranges to B pretty fast, and B is going to be much lower. B is a delocalized cation that's got some tertiary characteristic to it. That's a really stable carbocation. Like, all carbocations are higher in energy, and honestly, given where I'm drawing this now, I'm going to change this. I'm going to lower R down here a bit. All right. B is still really reactive. It's a carbocation. There's a carbon that doesn't have a full octet. It's very high in energy, not very stable. But B is way more stable than A. That's why the rearrangement happens. All right. Then nucleophile hits, and we get a protonated product. And this really is probably the hardest one to place and one I don't really care about that much. Sometimes the protonated product is a little higher in energy than the cation. Sometimes it's less. And then to get to the product, you lose that cation. And you get, honestly, you get lower in energy here. Right? The CO bond is stronger than the CI bond. So if you just look at this by bond strength, the product's lower in energy than the starting material. That's generally going to be true for SN1 and SN2. SN1 and SN2 reactions tend, at all temperatures, the product is favored. Okay, everybody. I guess the last thing, I get questions about this. The intermediates, the things you draw in a mechanism, are local minima. They're either global or local minima. See it? The peak in between is what's called a transition state. All right? Every elementary step has one transition state. And again, this is kind of esoteric for you guys, even at the end of the first semester. The difference between a transition state and an intermediate is detection. And so this definition has changed a little. There are a lot of reactions we used to think were one step. As technology gets better, you're like, oh no, that's 2 or 3 steps. All right? The question really is, does the molecule exist for some finite amount of time before it does something else? A transition state won't. Really, it's almost a ghostly thing that gets passed through. The intermediate actually is there. And so when you draw a mechanism like this, every structure needs to show up as a minimum on the reaction energy diagram. And like I said, you can do this experimentally or computationally where you don't just have this generic reaction coordinate. We would actually set something. We'd be like this bond length, that bond angle, something like that. And you'd plot actual energy. Right? There'd be some number like 72.15 kcals per mole. There's no way to do that just looking at structures in here. Okay? So now what I'd like you to do, put B res on this diagram. Take a minute and put this B res structure down here. Got it? This goes back to me being pedantic about resonance structures. B and B res are the same molecule. All right? There's just one molecule. You can draw them either way. So B res goes right here. Same place. Now, that's not the alternate product. Sorry. C, that's. So now, yeah, put the alternate C and put the alternate P on your diagram. I'm testing your young eyes. It's gotten pretty cluttered on there. All right, so C alternate and C are different structures, right? They're constitutional isomers. They're both protonated ethers. So again, an ether is going to be a carbon-oxygen-carbon functional group where neither carbon is a carbonyl. That's an ether, E-T-H-E-R. They're both protonated. So is the alternate C, is the green C going to be below or above the blue C? How come?
Would it be because it's less like hindered by everything else with the factor?
It's not the hindrance around the oxygen so much, it's the alkene, right? If you look, the big difference is the alkene. So you've got a monosubstituted alkene, a tri-substituted alkene. So the tri-substituted alkene is a little more stable. And again, on this scale where, like this is the difference between a neutral closed shell reactant and a secondary cation, that's going to be something like this, right? I mean, it's going to be a really, really small difference. And then the same thing is going to be true for the alternate product. The alternate product, you're just losing the proton, so we're going to have a monosubstituted alkene versus a tri-substituted. So it'd be something like that. So you'd probably expect to get more of the alternate product than you would the one I drew initially. If you remember, I created that problem like standing in front of you, so I didn't predict the product right. Yep.
Can you do a question where you have to write the rate law?
Definitely can have that kind of question. So what's the rate? Yeah, go ahead and write the rate law for this question. What does this reaction look most like? Which kind of mechanism does it look most like? SN1. Right? So it's a substitution. It's obviously not a straightforward SN1 because there's been a rearrangement. But as you guys look, if you guys think something should be SN1 or E1, that requires a carbocation, and anytime you guys have a carbocation, you should be thinking about a rearrangement. Basically, you're going to make a cation. If it can rearrange to make a more stable, cation, it's going to probably do that. Okay, so leaving group leaves, nucleophile comes in. That looks like an SN1 reaction. It's just there's a rearrangement in the middle. SN1 and E1 are called SN1 and E1 because there's only one molecule in the rate law. It's a first order reaction. So the rate law for this is just some rate constant times the concentration of A. It's not A, R, sorry. Okay, this is the slow step and the one that determines the rate. Like I said, this is why the leaving group being a better leaving group affects the rate. If iodide is on there, it comes off fast. If chloride's on there, it comes off a lot slower. So that's ahead of the rate limiting step. Methanol being a better nucleophile doesn't change anything, right? Like if methanol is a slightly better if it's water or if there's more methanol, it doesn't change anything. Yep.
Well, and if it was SN2, do the reactants, and then whatever is like.
Yeah, but if and so SN2, like the only way, let's see, methanol gets involved here. So if this last step were the slow step, like it clearly isn't, right? But if this step was the slow step, methanol would have to be in the rate law because it would be involved before the rate limiting step. As you look at a multi-step reaction, every reactant or catalyst or acid or base or whatever that participates before or during the rate limiting step has to be in the final rate law. All right? Anything that only participates after the slow step doesn't appear. See a couple of people packing up. I think we only have like 2 people signed up for 6 o'clock, so if you guys want to stay, you're welcome to stay. You don't have to. I'm not kidnapping anyone. So. Hydrates. Did I put hydrates on the topics? What a bastard. But thanks for telling me that. So seriously, I didn't really talk about hydrates a whole lot. Hydrates are really unlikely to appear on exam 3. See ya. All right, so let's do this under acidic conditions. So got a ketone, turn that into an enol under acidic conditions. So I wrote no strong bases there. This reaction is being run under acidic conditions. All right, this one's pretty obviously under acidic conditions. H3O plus is an acid. It's a really good idea anytime you draw a mechanism to think first, like, is this reaction under acidic conditions or basic conditions? It's not always going to be clear-cut. Sometimes it's sort of under neutral-ish conditions. But if it's under neutral conditions, you can't really have a strong acid or a strong base, right? If it's under acidic conditions, you can't have a base. So you're not going to like add HCl to your reaction and form a lot of hydroxide. All right? So if the reaction's being run under acidic conditions, your mechanism should include weak bases, weak acids, strong acids. All right? You're going to have some bases in there, but they can't be strong. We'll do a base catalyzed reaction in a minute. If the reaction's under strongly basic conditions, you can't have a strong acid, right? You can have strong bases, weak acids. It doesn't mean you're going to get the mechanism right, but you're not going to, if you keep the right number of bonds to atoms and you don't have a reactant in there that just simply can't exist under the conditions, I'm not going to freak. Like, I will see that. Anyone who teaches organic will see that from a mile away. All right, 5 bonds to a carbon, leaps off the page. You write hydroxide in this reaction, that's going to leap off the page. So make sure you're working under the right conditions. Okay. We've got to add a hydrogen to oxygen. We've got to take a hydrogen off of the carbon, and we've got to move the double bond. Like I said, if I go in and I take the hydrogen off the carbon first, I wind up with a really strong base. That can't happen. So first thing let's do is protonate the oxygen. I'll set this up to put that hydrogen in. So now I've got a strong acid, right? If I protonate the oxygen, I've made a strong acid. So one strong acid, H3O plus, facilitates the formation of another strong acid, the protonated ketone. And now I've got water in here. Water can actually finish this up. So water can grab the H. Remember, we have to take an H off this carbon. It's got 3 here, 2 there. So you've got to move that H at some point. Water takes that proton. We're going to use the CH electrons to make the new pi bond, and then we're going to use the pi electrons between C and O to neutralize the charge on oxygen. You can think about this, you can think about the protonated ketone as a carbocation. Right? Resonance structure of the protonated ketone is just a carbocation with an O on it. That's a really stable carbocation. It's tertiary. Plus, one of the things bonded to it, the oxygen, has a lone pair that can help stabilize that carbocation. And then this taking the H here winds up just looking like the last step of an E1. Right? Water takes the beta proton, you get an alkene. So now, do the reverse react. Draw the mechanism to go from the enol to the ketone under acidic conditions. All right, so the reverse reaction The reverse mechanism has to go through exactly the same intermediate. There's only one intermediate here, the protonated ketone. So that's got to be the only intermediate on the reverse. Well, so here we're going to protonate the alkene like you would protonate any alkene. The OH is actually making that alkene really electron rich, right? The OH is pumping electrons by resonance into the carbon-carbon double bond. Grab that H, and there you go. That's exactly the structure I drew over here. Protonate the alkene, make the most stable, right? Markovnikov's rule says you're going to make the more stable carbocation. That's going to be the tertiary. And now I guess I should put this in here. All right, now water is going to take the H that's on the O, and that will get us to the ketone. Since you asked about it, that's the hydrate. So any carbonyl, any CO double bond has a hydrate equivalent, which is just adding water across the carbon-oxygen double bond, like you would do for adding water across a carbon-carbon double bond. So using the mechanism on the board, show me how you'd get to the hydrate. Like I said, I know I said this probably won't be on the exam. I'm not going to focus, but you asked and I put it on the topic, so. And I know you're all keenly interested in Orgo 2 topics. All right, so from the carbocation, I'm just going to redraw my all right, so you've got that carbocation. If the reaction's in water, if there's any even trace of water around, water can add into the cation. Again, the main reason I wanted to show this, be really careful. When you add water to carbocations or alcohols to carbocations, add the alcohol, add the neutral water, the neutral alcohol. Under acidic conditions, that H is going to come along for the ride. So the initial adduct's going to have, like water attacks the cation, but both H's are still there. And then finally water can take that and you get the hydrate. All right. That's acid catalyzed reactions. I'm going to do base catalyzed a little more directly. Like I said, you need to be able to draw the keto-enol tautomerization, base or acid catalyzed tomorrow. You might well see it, or at least parts of it. And so, you know, you definitely need to look at this tonight, but also carbonyl chemistry winds up being really important next semester and in biochemistry. So if as you think about proteins, proteins are connected by amide linkages. That's got a carbonyl in it. How they're made, how they're hydrolyzed, some of the stuff they do involves carbonyl chemistry. So this sort of is generally true. All right, so like I said, I'll try not to belabor this one so much. Base catalyzed reaction. So here, can't have any strong acids. Got hydroxide in there, you're not going to make H3O+. All right. So, like I said, again, anytime you're given a mechanism, if you just don't, like I know a lot of you are trying to memorize mechanisms, and I don't blame you. As I've said over and over, memorization has gotten a bad rap the last 20, 30, 40 years in education, all right? Some memorization is important. You've got to have some stuff in your brain to work with, do all this critical analysis we want you to do, right? But you're getting to a point in science classes, and really from here on out, you're never going to be able to just memorize everything in a class. So you can't possibly memorize every mechanism I can ask you. So you might get lucky tomorrow or on the final exam, and it's like you've totally memorized one, and I asked it, and it's just like, cool, I just write it down. Congratulations. Like we all need to get lucky sometimes. But if you don't, ask yourself, the way to analyze these is what bonds break, what bonds form. What leaves the molecule, what comes into the molecule. And you can write that out on the side. I need to break this bond, I need to make that bond. This thing moves. And then try to construct a plausible sequence of those things happening. So, again, in this one, right, this carbon's got 3 H's, that carbon's got 2 H's. We have to take a proton away from that carbon. Have to. If your mechanism doesn't take a proton from that carbon, like one thing with the line structure that I see you guys do, not you people in the room, just Orgo students in general, is you forget that there are 3 hydrogens on that carbon. Right? And you'll just draw a line to it, like I want to make a bond there. Right? You can't just do that. And I get it during a test, like you're rushed for time and it's easy to forget stuff, but always keep tabs on how many hydrogens are around. 3 hydrogens there, 2 there, so we got to pull 1 off. So draw it in there. And then the other is we have to put a hydrogen on the oxygen. So up above, that was the same thing. Pulling the hydrogen off with a base, right? That's an acid-base reaction. That's going to make a conjugate base, and it's going to make actually a really strong base. Okay, so we couldn't do that up top because the reaction was run in acid. Putting a proton onto the oxygen, if we do that first, we're going to make a strong acid. That's what we did up top. The reaction up top was run in acid, so making a strong acid is fine. When we're in base, there's nothing that can put a hydrogen there right now. And if I put a hydrogen there, I get this structure, which is a really strong acid. I've got hydroxide sitting around. There's no acid that can protonate that oxygen. Second, I'm going to have a strong acid and a strong base. They'll just react. So now the thing to do is take that hydroxide, pull that hydrogen off, and we get what's called an enolate. Negatively charged carbon. That should jump out at you as being a really strong base. But it's resonance stabilized, which helps a little bit. And the enolate, actually, if you take a picture of it and measure bond lengths, it looks more like this. Taking a picture of it's really complicated. But the carbon-carbon double bond looks like a double bond, has a double bond length. Carbon-oxygen bond has a carbon-oxygen single bond length. The 2 carbons are both sp2 hybridized. They're trigonal planar. And from this resonance structure, it's really clear how we get to there, right? From the C- resonance structure, it's not as clear how we get to the enol. But now we need to put a proton on the oxygen. And now the oxygen is negatively charged. Now it's a base. So I don't have to make a really strong acid to protonate it. That O- can just grab a proton from any weak acid. And there you go. Another thing on mechanisms to keep track of, as you notice here, I've drawn equilibrium arrows and a resonance arrow. If 2 structures are resonance structures, do not tell me they're in equilibrium. Right? You're not in equilibrium with yourself. You're always yourself. So that's what you want. 2 different versions of you, resonance arrow. You and your brother, you and your friend, you and Dougie down the street, equilibrium arrows. It's a bad analogy. It works better for yourself. Yeah, Matt.
Because you have resonance, could you just go straight to 190 parts on oxygen?
You could, yeah. So again, the other nice thing there, it sounds like I'm giving you all these things not to do. The nice thing here is, well, if you're drawing a mechanism, if you only show me that arrow, you need to draw the C minus. But yeah, you could do that and go to the O minus. Anytime you involve sort of the same thing over here, right? Like in this mechanism I did over here for the energy diagram, I'm trying to get to this product that's got the methanol added to the tertiary carbon, so I need to draw cation B. I don't have to draw the resonance structure of B. I don't have to mention it at all. But if I had drawn the alternate product, right, I would either need to show this resonance structure or add some other arrows in there. But any time you're talking about a molecule that's got resonance structures in a mechanism, you don't have to show me all the resonance structures. You can just use any one you like. Just make sure the curved arrows match up.
Kind of on a similar question, then going back to the acid catalyzed one. Would you ever do the double bond going up to the oxygen to make that negative?
Where?
So like, you know how you have the oxygen attacking the H plus?
Uh-huh.
You just do a resonance structure there and put a negative charge in the oxygen and positive on the
You could. It's not, I mean, so you're basically saying, would you do, let me see if I have you right. That? I mean, you could. Well, if you drew me this arrow, probably in Orgo 1, I don't say anything bad about that. So short term, yeah, you could do that. And certainly if it helps you think about it, that's not a bad thing to do. But typically when we draw mechanisms, your starting point and your finishing point, you draw the most stable form. I think that comes up more on products. I see people, and there you're kind of screwing yourself up. People will get to a resonance form of the product and then be like, and then it goes to the product. It's like, no, you've already done it. Like it kind of is deceptive that you think you need to do something else and you don't. You've finished. But yeah, there's nothing really wrong with it, no.
So did you say that hydrates were just for Orgo 2 or?
Yeah, I'm not going to ask you any hydrate questions. I mean, I didn't realize those topic lists end up a lot of times being copy-paste jobs as well, and sometimes I talk about them and sometimes I don't. I mean, they are, so like I said, kind of the fundamental thing, if you're going to take biochemistry someday, carbonyls, carbon-oxygen double bonds, all of them, if they have a proton on the atom bonded to the carbonyl, they have an enol. And regardless of what is bonded to the carbonyls, there's always a hydrate. And that, the equilibrium, like, I guess I should say that, in fairness. So we've kind of got, all right, all these are in equilibrium with each other. If I go upstairs and I bring down a jug of acetone, and I've got like a mole of acetone, I've got maybe 10 of these and 4 of those. I don't mean 10 to the, I mean, if I have a mole, I have like barely any of this, 10 to 100, 1 to 10 of these at any given time. So the equilibrium really favors the keto form almost always. But the chemistry, and this is kind of a weird thing about them, the chemistry will sometimes rely on the hydrate or the enol doing something. Sorry?
Is the stuff we just did in the test model, is that multiple times?
the keto-enol stuff could be on the test tomorrow, yeah. The hydrate bit, evidently I put the word hydrate in the topic on the study guide, and I'm not going to ask you hydrate questions, but the keto-enol interconversion might show up in some form, yeah. You bet. And it comes out of chapter 9 where you add water to an alkyne. So when you add water to an alkyne, you get an enol. That's what you get. And then instead of adding water again, like that's a reasonable thing to maybe show you. All right, so if I take, yeah. So if I add water to an alkyne, do a Markovnikov addition, I get the enol that we've been talking about. If it's if it's propyne, yeah, H plus or mercury. I mean, I won't ask this mechanism because it's a bit more complicated than it is for an alkene. But once you get here, like if we did this again, we would get the hydrate. You'd sort of expect to get the hydrate. That's why the hydrate's usually on there for this list, yeah. So if you add HX to an alkyne, so if I do this, if I add HBr, all right, I actually get that, and then if I add HBr again, I get 2 Brs on there on the same carbon, and the H's go on that other one. Like that actually does happen with HBr, HCl, HI. With water, though, you get this enol, and like I said, you might even get some hydrate. But mostly what you're going to get is the ketone. Anything else? Yep.
Well, I have a question regarding one you already did.
That's fair enough. What's up?
Oh, okay. The one you did behind right there.
This one? Yeah.
You wrote what else? Does that just mean like the enantiomer of it?
No, what else is this? So this mechanism goes through this cation. Well, first of all, iodide leaves, you make a secondary cation. That rearranges to a tertiary delocalized cation. I was making the point that this delocalized cation, either of those carbons can react as the positive carbon. Right? So the nucleophile can hit the tertiary carbon, the nucleophile can hit the primary carbon. And you get 2 different products out of that. And if you'd seen that in real time, I drew the product. Somebody asked about doing a reaction energy diagram, so I wanted a complicated mechanism. So I drew the product, kind of stood back, let you guys work on it, and realized, oh wait, I bet it would give something else. So I threw that on there. I threw that on there trying to appear like I designed it that way, but it's not. Yeah. Yeah, I mean, in terms of questions for tomorrow, that is probably high on the list. I mean, sorry, that makes it sound like the whole exam's radicals. That'd be hilarious, wouldn't it? So I get this, I mean, like seriously, being serious for a minute. I haven't put much from chapter 10 on there. Same with chapter 5. I did this EE stuff, and now I've got people like coming to me, digging deep for EE questions. Same on radicals. Here's what you need to be able to do for radicals. That. Chlorine can go anywhere, but they're all the same. That. So bromine's more selective. If we actually did this reaction with chlorine instead, Like you'd end up with some chlorine. You'd have a lot of chlorine there, but you'd have some chlorine there, and you'd have some chlorine there, and some chlorine there. You might even get some on the methyls. Chlorine, by the way, if anybody, like who knows what your future holds, right? If anybody ever asks you to work with chlorine gas, find a new boss. Like that stuff, well, or be a trained chemical engineer or something. Like chlorine gas is pretty nasty. The other thing you should be able to do is rank radicals in stability. Yeah, so rank those 4. And that's it. No mechanisms. Sorry. Come stand in your way. If it helps. So when you're trying to judge a radical stability, you can just think of it as a cation. All right? It's not. The radicals, all 4 of those radicals are more stable than the cation below them. But the order of their stability will go exactly the same way, right? A radical is a carbon that doesn't have a full octet. A carbocation is a carbon that doesn't have a full octet. So the way you rank their stabilities will be the same. And as you're looking at this, we got think about it, secondary, this is localized, right? That radical's on that carbon. You can't move the radical center anywhere else. Tertiary, localized, all right? It's too far away from the double bond, separated by 1, 2 sigma bonds from the double bond, so there's no way to delocalize it. This is tertiary and delocalized over 5 atoms. All right, I can move it, I can put the radical there, and I can put the radical there, and move the double bonds at the same time. So if you're doing these, right, the tertiary delocalized is more stable than the tertiary localized. That's more stable than the secondary localized. So what about the one down on the end? The way I've presented this, you should probably think that's either going to be the most stable or the least stable. That's not really a way to answer the question tomorrow if this were the question. But right now, the way I've done this. All right, so this is, if you want to think about it, it's primary, but it's not even really primary. This is an sp2 radical, or as we would call them, a vinyl radical. The hybridization down below, this would be an sp cation. All right, and so the more S character an orbital has, the more electronegative it is. So an sp anion is more stable than an sp2 anion, is more stable than an sp3 anion. Cation goes the reverse. sp2 cation is more stable than an sp2 cation. So this one is the least. Having that radical on a carbon-carbon double bond. And there's no resonance here. A lot of times people are like, oh, there's got to be resonance there. And you get all those pi bonds. It looks like there should be resonance, but there's not. If you wind up with that radical center on the double bonded carbon, there's no way to delocalize it anywhere.
You erased some columns earlier.
Hang on just a second. So that's basically it. You need to know the radical reactions, predicting the product. You need to be able to estimate the stability of the radicals. Sorry.
I was going to ask if you could do like an example of substitution with like a percent E.
Yeah, the one I just erased.
Yeah, exactly.
Should have erased that one. Yeah, let's see. See it? Yep.
Also, did you get a calculator tomorrow?
Nope. Just to make it more interesting. All right, there's the. So if I take the brom, oh, I haven't given you enough, have I? All right, we start with the bromide on the left, do a reaction with it, we get two products. Tell me the EE of the first product I've shown there, and give me the stereochemistry. Give me a mechanism for the other product, and give me the percent EE. All right. So is the azide the N3? Is that behind the board or in front of the board? Or 50-50? Yeah. Yeah. So what's the mechanism? It's not E. It's SN2. Azide's a good nucleophile. It's not a real strong base. DMF's polar A product. It's cold. So this is going to be SN2. So if it's SN2, where's the azide? Azide is going to be in the back. What's the percent EE? Yeah, I mean, that's probably what I'd be looking for you to say on this one. I will never, I can tell you, I'm being silly at this point, 90 minutes into a review session, that you're never going to get an EE. You can't measure an EE that accurately. But if this is an SN2, like I said, N3 is not a good base. It's a fairly weak base. It's a really good nucleophile. It's this cool looking molecule. It's kind of like ozone, actually. So it's on both ends, it's got this, it's kind of bullet shaped. And so it's like a missile. It's got just sticking these electrons out in front of it. So it's a weak base, good nucleophile, it's good at SN2. Polar aprotic solvent, low temperature. This is likely to be near enough to a pure SN2, which means in a pure SN2 reaction, whatever the EE of the starting material is, that'll be the EE of the product. What's the EE of the other product? That normally would be a good answer. It is a trick question, but it's not a trick question the way you think. Zero, why is it 0? Why do you say 0? It's not an SN1. Sorry? Why is there's not an enantiomer? This is not a chiral molecule. All right? No chiral center. We lose our chiral center here. There's no chiral center in the front. So that. Is it SN1? That's actually not a bad question. Yeah.
So I was wondering the same thing, and I noticed that if the leaving group leaves, then you can do like a resonance structure.
Exactly.
I don't know if that.
No, that's good. And so that it occurs to me. I was remembering a question on an old exam, and I did not give you enough. I probably didn't give you enough information to answer the second one. To tell me what mechanism it is. So given what you've seen here, saying that it's SN1, here's the thing that would happen though. If this comes about by an SN1 mechanism, this EE shouldn't be the same. It should be less. Like this would be one of those where you're kind of doing in between. But SN1 is a good, let's do the SN1 mechanism and then I'll show you the SN2 prime mechanism. Okay, so SN1, and there goes your stereochemistry, right? We've lost the chiral center. There's no longer, that cation's not chiral. So now the product, if azide hits here, or if it comes from behind, we'll get racemic middle product. But now, well, and you can, like I said, there's a resonance structure here, and I'm glad some of you saw that. And that's kind of like the one I erased over here. And so we can have N3 just attack the primary cation, that takes us up there. Or you could draw it like this. Guess I should show a minus. You could draw this from either resonance structure. Just it takes one more arrow from one of them. And yeah, given the information I've provided, that actually is fine. Like, I think in the question, I hope I remember the question right, I actually gave a rate law. So if I told you that the rate here was, for both of these, right? That it's dependent on both of them, that is not consistent with the SN1. So for what I told you, saying SN1 is fine. This is called, and this has shown up as kind of a tricky question or a bonus question. This is a reaction called the SN2 prime. So N3 hits the primary the less sterically hindered carbon down here, pi bond, kick out the leaving group. It's kind of akin to an E2. That pi bond is sort of interacting with the sigma star of the CBR. All right, and so the reason this might happen, right now the azide, the nucleophile is hitting an unsubstituted carbon. Here it's going to hit the more substituted carbon. And in fact, if you do this, you'll see this a lot more if it's like this. All right, so that molecule, you can't do SN2 here, but you can here. So you'll see that some there. Of course, you can also do SN1 really well here too, so that both mechanisms come into play.
On that one more to kind of block behind you, you did like both C3H3 attack and that other part.
Yep.
Yeah, can I ask why? Why would it just attack the geometric?
Because so strong base grabbing a proton versus a strong base making a bond to a carbon. The H is more accessible. So that's going to be reversible, right? That H is kind of going to hop back and forth. But when you get down to this O minus, it's a good nucleophile basically sitting right next to an electrophile. So that just hits. Yeah. Yeah. I have to admit, I'm pretty gassed. So this recording I'll go upstairs and start uploading this. So John, you came in late. Actually, anyone who came in, I know a few people have come in. Some of the EE questions, and you asked about a calculator, and some of the EE questions at the beginning were about how involved those are going to be. Not very. Like the EE is only going to be in regards to substitution problems. All right, so I'm not going to ask you guys, it's not going to be one of the chapter 5 questions where you have to really dig in and figure out an EE or use specific rotation. The plus minus bit is important and may show up on the final. That's part of nomenclature. But yeah, you're not going to have to, the more quantitative problems I'm not going to do. The same on 10, so 5 and 10, there's really not much from either 5 or 10. Nobody should spend hours and hours tonight going over EE questions or radical mechanisms or anything like that. So it's 7 and 9 basically. Any last business questions real quick? Okay, so I'm turning off the camera. Seriously, guys, I know you have a lot of stuff going on this week, and next week's busy. Get some sleep tonight. When it stops raining, go for a walk. Eat right. Drink right.